What questions do you have? Questions? Things going all right?
Okay, good. Homework's due Friday, right?
Homework is due Friday, yes. No, it's due right this second. No, Fridays. Yeah. Friday works.
Looking through our notes, I'm like, oh, I don't have notes on this.
All right. So let's finish up our discussion here of transformations as far as kernel and range goes. So we talked last time about determining whether or not a linear transformation was one-to-one, and we said we can determine that by looking at the kernel of the transformation. What does the kernel have to be if it's going to be one-to-one? 0, right? The only thing in the kernel is the 0 vector. We know that certainly the 0 vector is always in the kernel. The linear transformation always maps the 0 vector of your domain to the 0 vector of your codomain every single time. So that's always in the kernel. And if it's one-to-one, that can be the only thing that's in the kernel, period. And then vice versa, if you know the kernel is just the 0 vector, then you know that it had to be one-to-one to start with. Going back to thinking about realizing transformations through matrix multiplication, which is where we're going to head to today, with doing basically every single transformation through matrix multiplication. What did that mean for the reduced row echelon form of your matrix and transformation? What did you have to see? Close. That would be if it was if the domain and the codomain had the same dimensions. What do we need to see when we do the reduced row echelon form? Is going to be one-to-one. Yeah, pivot over a column, right? We need the null space to just, or we need the kernel of the transformation corresponds to the null space of the matrix of the transformation. If we want the null space just to be the 0 vector, then we need no free variables. So we need pivots in every column. Okay. So let's flip-flop that. We know that we've already defined what we mean by T being onto, but let's just redefine it. And I don't know why I didn't leave enough space here for that, but we'll do it off to the side. Remember, if it's onto, that means if I pick anything in the codomain, there's something in the domain that maps to it, right? So, whoa, why am I still in red? That was weird, and why did that jump on me? Why are you being a pain? Okay, fine. I'll do it this way. Sorry. All right, let's try this again. If for every vector in W, there exists a vector in V such that T of V equals W. And we refer to, if we think about the image being what you get out of the function, then what you put into the function is called the pre-image. So it just says that every vector in W has a pre-image under the transformation. And so V would be a pre-image of the W vector. All right, anyway, let's think about how we can tell if a linear transformation is onto, again, from a language of finding a matrix. That's our goal here, is to realize all transformations as matrix multiplication. That's our goal for today. Okay. So a minute ago, we just said you can tell if a transformation is one-to-one by looking at the reduced row echelon form and get a pivot in every column, right? But when we think about one-to-one, remember one-to-one means that basically we can solve this equation all of the time, right? No matter what, we can solve that equation, no matter what we put on the right-hand side. Again, if we think about this as matrix multiplication then, and let's make this an X because I'm trying to solve it. If I want to make sure that this is consistent, this matrix equation is consistent for every single vector that I put on the right-hand side, what do you need to see when you row reduce T? A pivot in every row, right? We need to make sure that the column space of T is all of W, right? We want to make sure that if we want to show that it's onto, we want to make sure we get a pivot in every row that's going to allow us to solve this all the time. Or remember, the range can also be thought of as the column space of the matrix, right? We want to make sure the columns span the codomain. That's basically what we're doing here, right? So we can tell the linear transformation is onto if we row reduce the standard matrix, whatever that standard matrix needs to be. And actually, we're going to talk about matrices relative to bases, so it may not be standard or not. But we row reduce the standard matrix and get a pivot in every row. Is that okay? All right. So this actually allows us to add a couple of conditions now to our mega theorem. So what letter are we on for that, by the way? I don't even remember at this point.
The last one was 20.
What?
The last one was 20.
20? Okay. Well, got a few more. All right. So remember the notation. If we use T sub A, remember we're showing things that are equivalent to the condition of A being invertible. T sub A means the linear transformation. Actually, if we go from a space to itself, we refer to that as a linear operator. So this would go from Rn to Rn, defined by T sub A of X is just multiplication by A. Okay. So for every matrix that you have, there's a natural transformation. Every M by N matrix that you have, there's a natural transformation that goes from Rn to Rm. That's done by matrix multiplication. When we write T sub A, we mean that in this case. So in this, for that mega theorem, this just means that we're talking about the linear operator going from Rn to Rn. So then 21, that would be our next number, is that linear operator, that linear transformation is 1-to-1. Because again, how do we check if something is 1-to-1? We row reduce it and we see a pivot in every. For 1-to-1 is column, right? For 1-to-1 is column. If we see a pivot in every column and we have a square matrix, that means we actually see the identity matrix in that point, right? Okay. So 21 is T sub A is 1-to-1, but we just proved a little bit ago that being 1-to-1 is equivalent to having the kernel equal to 0. So that's another equivalent condition. Another equivalent condition is that the transformation defined by A is onto. Because again, how do we check if something's onto? We row reduce it and look for a pivot in every row. But again, if the matrix is square, a pivot in every row means it had to be the identity matrix, right? And then in the language of range, this would tell us that the range of T of A is all of Rn. The range is everything. That's what it means to be onto. We're going to have 2 more to add to this in a second. So keep your mega theorem sheet nearby because we're going to have 2 more that we're going to label on here in just a minute. All right. So anyway, this gives us more equivalent conditions to a matrix being invertible. It's kind of fun. All right. Let's scroll down to the next bit here. Oops. I think my thing moved on me. Yep, it did. There we go. I don't know why those sheets move. That's all right. Probably need to get better software than OneNote to do this. Anyway, all right, so we've got rank and nullity of a linear transformation. But we've already talked about rank and nullity of a matrix, right? So we're going to change that over to the ideas here for transformations and switch words around, but they all mean the same thing, okay? What was rank of a matrix again? How did you find the rank of a matrix? Number of pivots total, right? Okay. All right. So when we're looking at pivots, we wanted to look at, well, the nullity was number of free variables, pivot less, right? So if we think about it in terms of linear transformations, the pivoted columns or pivoted rows are the ones that are going to give us something about the range. The pivot less are going to give us something about the kernel, right? So for a transformation, the rank of a linear transformation is, we write it as rank of t, and that's going to be the dimension of your range of the transformation. That's the definition. Again, the way we're going to check rank of a transformation for our purposes is that we're going to find a matrix that represents the transformation. We're going to row reduce it and count the number of pivots. Okay? Just like we did for matrices. Okay? But for in the language of transformations, the rank is equal to the dimension of the range. Which makes sense, right? Because we've already equated range with column space, right? Which again tells us the number of pivots, doesn't it? So then our nullity of a transformation, which again, there's not really a nice abbreviation for nullity. It's just nullity. It's the whole word. Okay. This is going to be the dimension of your kernel of the transformation. And again, the way we find the kernel of a transformation, the way we've been doing it, is find a matrix for the transformation, row reduce, and then write a basis for the null space. So nullity is the same idea that we had back when we did it for matrices. Everything comes back. All right. How are the rank and nullity of a transformation related? Well, we talked about this back in the language of matrices again. The rank of a matrix plus the nullity of the matrix had to equal what? Well, the range was the column, or the rank was the dimension of the column space, and nullity is the dimension of your null space. When you add those together, we had to get number of columns, right? Yeah, number of columns, right? So we get the number of columns. Is that what you said the first time, and I just didn't hear you?
No.
Oh, okay.
I got it wrong.
Okay, that's fine. I just want to make sure I didn't correct you for no reason. All right, so rank plus nullity was number of columns, right? What gives you number of columns in the matrix when we do this for transformations? When we were doing that from T to Rn to Rm, what gave you the number of columns? The n did, right? For Rn, this is the dimension of your domain, right? Right? So if I've got a transformation going from V to W, the rank of your transformation plus the nullity of your transformation must be the dimension of your input space, the dimension of your domain, not the dimension of your range. It certainly can't be the dimension of your range, because where is the dimension of the range already in this equation? The rank. The dimension of range is right here, right? So it can't be dimension of range or dimension of codomain on this side. It needs to be the dimension of your domain on this side. Sounds like a good true-false question. That might be a hint. Okay, it sounds like a good true-false question, right? All right. In any event, that's how we do that. So let's answer these questions here. These questions all involve that equation that we just came up with. The transformation from R5 to R7 has rank 3. What does its nullity have to be then? 2, yeah. So from the original equation that we have, it says the rank of the transformation plus the nullity of the transformation has to be the dimension of your domain, which in this case is R5, right? 3 plus nullity equals 5, so the nullity is 2. Does that make sense? Literally just using the equation here, right? Same idea. In this case, rank of the transformation plus the nullity of the transformation has to equal the dimension of what in this case? P4, right? Yeah. They tell us the rank is 1. What is the dimension of P4? 5, right? Remember, it's always one more. Because to be able to generate 4th degree polynomials, I have to generate an x to the 4th, an x cubed, an x squared, an x, and a constant term, right? That's why there's 5 dimensions instead of 4. So for this one, then, your nullity will be 4. All right, the next one's just changing the words around, making sure you understand what the words mean. The range of t is R3 in this one. Well, let's talk about different words that we might mean that. If the range is all of the codomain, we say the transformation is what? Onto, right? This is onto, since my codomain is my range, right? We want to use this rank nullity equation again to figure out the answer for the nullity. What is the same thing as the rank? What is the definition of rank for a transformation? Dimension of the range, right? In this case, the dimension of the range is 3, right? Because R3 is the range, the dimension of the range is 3. So what does the nullity have to be? 3 as well. Good, because it has to add up to 6, right? Right. So for C, the range of your transformation is R3, so your rank of the transformation is 3, right? So this is going to give you that your dimension, your nullity of the transformation is also 3 because the dimension of your domain space was 6. Let's look at the last one here. They tell you the dimension of the range is 3. Dimension of the range is 3 tells you what about the transformation? Rank is 3, right? Dimension of your domain is 4. So the nullity has to be 1. Good, yeah, good. So for D, then your nullity is 1. Is that okay? All right. So now I said we can go back to add a couple of conditions to your mega theorem. What are we on, 25 now? Let's do this in terms of rank of the transformation defined by A and the nullity of the transformation defined by A. Rank again is dimension of your range, right? But we already know that A being invertible is equivalent to the range, the transformation being onto. So if you have an n by n matrix, what does the rank have to be here? Which one? It's n by n. Which one does it? I mean, it has to be then n, right? Because it's the rank is the same as the dimension of the range. If it's onto, the range is all of our n. So your rank will be n. If your rank is n, what's your nullity? 0. Good. And notice it correspond exactly to rank and nullity of the matrix, right? All right. So this one asks some more conceptual questions about this concept. Illustrate some concepts here, and then we'll switch gears into doing more matrix stuff. So you actually do some honest to goodness examples, if you will. This one asks us for the smallest possible value for the nullity. So let's look at the dimensions of the two different spaces here. What's the dimension of the domain? 12. What's the dimension of your codomain? 10, right? Well, the best possible scenario for this transformation, if you, in some sense, is it's onto, correct? If it's onto, what's the rank of the transformation in this case, then? 10. Yeah, because it'd be the whole space, right? If it's not onto, the dimension is going to get smaller, right? Best case scenario, if there is a best, if you think about being as big as possible, right? Best case scenario is that it's onto, it hits all of P9, so the dimension of the range is 10. So what does the nullity have to be in that case? 2. Nullity can't get any smaller because the rank can't get any bigger, right? If the range is smaller, the dimension of the range just gets smaller, so the rank only gets smaller, which makes the nullity bigger, correct? So the smallest that the nullity can be in this case is 2. So since your dimension of your domain is 12, and since the rank of the transformation is less than or equal to 10, which is the dimension of P3, P9, I don't know where I got P3 from. We see that the nullity of the transformation is at least 2. So the smallest it can be is 2. In particular, can this transformation be 1-to-1? What does the nullity have to be if the transformation is 1-to-1? 0. So can this transformation ever be 1-to-1? No. I cannot, 1-to-1 functions, basically we refer to that mathematically as they embed things in other places. There's an exact, think of it as an exact copy, right? There's like a 1-to-1 correspondence with the domain and its output space, right? It literally takes it and shams it in there, right? So for example, what I mean by that is, here's the plane, right? Here's a copy of the reals. I can embed it that way. Here's also a copy of the reals. I can embed it that way. That's what I mean by embedding, right? I can think about the number line being here or lots of different places, right? If I'm going to stick something inside of something else, it can't have a bigger dimension than the thing I'm sticking it into, right? I can't stick all of 3 space into a plane, for example, right? I can smash it down, but it doesn't say space anymore, right? I only see a plane. Okay. So if it's going to be 1-to-1, I can't have my domain space be bigger than my codomain space. It's not possible, right? So if the domain of your, if the dimension of your domain is bigger than your codomain, it can never be 1-to-1, ever. Okay? That's what this is supposed to be illustrating. Well, let's look at this one. Let's go the other way. This one says, what's the largest possible value for the rank? Well, the dimension of your codomain space here is 10. So you might be tempted to say 10, but that would not be correct in this case. Okay. Again, if we think about a best possible case scenario, is that I take my domain and embed it over here. Right? If I'm going to take this space, which has dimension 6, my best case scenario is I took it and made an exact copy of it over here, which would have dimension 6, right? So the largest possible dimension I could have for my range here is 6. So the largest possible rank we could even possibly have here is 6. Okay? Think about it again from the language of matrices. If you were thinking about this in the language of matrices, if I were creating a matrix for this linear transformation, the domain space has dimension 6. Your codomain space has dimension 10. What size matrix would you have then? 10 by 6, right? It reverses it. But regardless, you can only possibly get 6 pivots. Right? I only can get 6 pivots. The biggest that my rank can get is 6. My row reduce, right? So in this case, since your dimension of your domain is 6, which is certainly less than your dimension of your codomain, we have that the rank of T is less than or equal to 6. Certainly your rank can't get bigger than your dimension of your codomain, but it also can't be bigger than the dimension of your domain. Right? It's bounded by whichever is the smallest of the dimensions. All right. So the previous example, we said that transformation cannot possibly be 1-to-1. The domain is too big. Can this transformation possibly be onto? Can I take a dimension 6 space and make it onto a dimension 10 space? I can make it onto?
No.
No, I can do 1-to-1, but I can't make it onto, right? The space is too big. Right? Now, if you've done, which I know you haven't, if you've done some countability ideas and arguments and stuff, there are 1-to-1 functions that would map that space to the other one, but they're not linear transformations. They're not linear functions. From a linear algebra perspective, the biggest dimension I can have for my range is 6. That means it's too small. So I can never be onto. So the moral of the story is, if your domain space dimension is bigger than your codomain space dimension, cannot be 1-to-1. If your domain space dimension is less than your codomain space dimension, cannot be onto. Okay? So let's see if we can answer those questions that are down here. We have a 6x4 matrix. That's how we're defining our transformation. What's the dimension of the domain space? If the matrix is 6x4, the dimension of the domain is 4. The dimension of the codomain is 6, right? Remember, it's reversed, right? Dimension of your domain is 4. Dimension of your codomain is 6. So which can it not be? Can it not be 1-to-1 or can it not be onto? Cannot be onto, right? Our codomain is too big. Does it have to be 1-to-1? No. I can map everything to the 0 vector, for example. Definitely not 1-to-1. right? May or may not be 1-to-1, but it can be 1-to-1, but it cannot be onto. If your dimensions were reversed, here, then it wouldn't be 1-to-1, but it could be onto. If the dimensions were reversed. The answer would be reversed in that case. What can we say about the rank and the nullity? Well, what I'm asking about that is, if you have a 6x4 matrix, let's think about it in terms of pivots. What's the maximum number of pivots you can have with your relative if it's 6x4? 4. So the rank is at most 4, right? It's the biggest the rank could possibly get, right? So that's what we can say about the rank. Can't say much about the nullity except that it's not any bigger than what? Well, I guess we can say a little bit about the nullity. Can't say much about the nullity because it's possible for it to be 1-to-1, right? You said it was possible to be 1-to-1, but can't be onto, right? So the best we can say is that the nullity is bigger than or equal to 0, less than or equal to 4. About all we got. Does that make sense? Let's ask the reverse question, and I think that's the last one on this handout, so I'll have the new handout here for you in a second. What if we reverse it? Have an 8x13. Dimension of your domain then is, dimension of your range is, or codomain is 8, right? Domain is bigger than range, or codomain. Can it be 1-to-1? No, it can't be 1-to-1. As a matter of fact, what does your nullity have to be at least in that case? 5, right? And what that says is that, if you think about it, I don't like to think about it geometrically, except it's hard to imagine things that are dimensions that big, but what it means is that I have to lose at least 5 dimensions to map from 13 to 8, right? So, for example, if we think about the R3 going on to R2, I lose at least 1 dimension. Which makes sense if you think about it physically, right? If I take everything in space and smack it into a plane, I lose at least 1 dimension, but I might lose 2. I can take all of space and put it on a line. That would lose 2 dimensions. Or I can take all of space and take it to 0 and lose all 3 dimensions. Does that make sense? Okay. Cannot be 1-to-1, can it be onto? Sure, if the domain's bigger, I can make it onto, right? We can think about mapping all of R3 onto R2, for example, by just eliminating the z coordinate. Making the z coordinate 0, then everything gets smashed onto the xy plane. Right? That takes all of R3 onto R2. That's called projection. I could also smash it onto the xz plane by making the y coordinate 0, or the yz plane by making the x coordinate 0. There's lots of different projections we could do. Since it's 8x13, the biggest the rank can get is 8, and we already said that the nullity has to be at least 5. All right. Any questions about those at all? All right. So, since we've been equating this with matrices already, let's talk a little bit about matrices and linear transformations. I said that to you already, right? I thought about it again when I came to class. I'm like, oh, did I name all that? About me to do.
I did learn from our mistakes.
All right, switch it over here to my other handout. All right, so this one's, we've already alluded to this, and we've already used it a little bit, especially on our transformations that go from R3 to Rn to Rm. But we always did everything in terms of the standard basis, right? We basically plugged in the standard basis, got outputs, and then used the coordinates from the standard basis of the codomain space to fill out our columns, right? We did that before. We'll go into it as we go along here. But here's the idea of how we do the matrix for T relative to B and B prime. I'm going to hate the notation here. The B prime is the basis for the codomain. Your B is I hate this notation, but it makes sense if you think about the way the matrix is formed. The B prime is your basis for your codomain. Your B is the basis for your domain. Remember that the dimensions get reversed, right? When we make the matrix. That's why they have this notation also looks reversed. I think it looks reversed, doesn't it? Okay. In any event, here's how you make the matrix. Remember that the reason why we have a basis is because we can write everything in the space in terms of the basis vectors as a linear combination, right? It's the whole reason why we have bases. So it gives us a finite set of, well, for our purposes, we have a finite set of things that we can use to describe everything in the infinite space. There are also infinite dimensional vector spaces, but we're not dealing with those. Okay. All right, so here's how we fill it out. And this is exactly how we fill out the columns. All right. So again, if we think about the dimensions, notice it says that I have n vectors in my basis. My dimension of v would be n. I've got m basis in my basis for m vectors in my basis for w. So dimension of w will be m. So we should get an m by n matrix when we're done, right? Okay. All right. So the way we do this is that we're going to take our vectors, and I didn't leave myself enough space. That's okay. I'll just zoom in and make myself have more space. I'm going to take each of my vectors. I'm going to plug them into my transformation. Again, if we know what the transformation does to the basis, then I know what the transformation does, period, to every single vector. We've talked about that, right? Because transformations break up over sums, constants pull out. So transformations completely break up over linear combinations. Okay, so it makes sense that I'm going to take each of my basis vectors for my domain and plug them in, right? Okay, but those may not be numbers, right? If I do a transformation that goes from P3 to M22, those aren't numbers that come out, those are matrices that come out, right? If I go from R6 to P7, then I get polynomials that come out, those aren't numbers, right? But we can change things into numbers by doing coordinates, right? So for each of these outputs, we're going to find the coordinates relative to the output space. So it's a two-step process. First, you plug in your basis vectors into the transformation. Then you take the coordinates of your of those outputs with respect to your output space basis. Now, if we want to realize all of this stuff through matrix multiplication, if I want to do T of x, whatever x happens to be, we will get the coordinates for that output if I take my matrix that we just found and multiply it by the coordinate vector of t, try again, of x with respect to b. This is how we can this is how we can realize any linear transformation of finite dimensional vector spaces through matrix multiplication. This is helpful if you want to work with computational software to do this stuff, right? Because it works much better with numbers than with letters flying around, right? All right, so again, the idea here is that, of course, if I want to use these numbers, I better have the x described as numbers, as a coordinate vector, right? Yeah. And then I can do the coordinates here. I have my matrix here. I multiply. It will give me the coordinates for the output. All right, so let's see how this works. We'll do several examples of this. All right. So, pardon me. We're given here two non-standard bases for R2 and R3. So this is going to go from R2 to R3 here, right? Agreed? Okay. So this one we want to find, pardon me, we want to find the matrix of T relative to B and B prime. So step one, calculate your outputs for the basis of the domain. T of 1, 3, T of negative 2, 4. Put in 1 for x and 3 for y, we get 7, negative 1, 0. Pardon me. Plug in negative 2, 4, and we get negative 2 plus 8 is 6, 2, 0. I believe I did those right. Yeah. Okay. So now I don't want to just take these and pop them in my columns. I need to do the coordinates of these with respect to my B prime. So remember, when we do coordinates with respect to a vector, with respect to a basis, I need to row reduce, right? I can do them both at the same time because it's going to be the same matrix here that I'm going to use both times because it's the same basis, right? So if you want to do this all at once and put it in your calculator, I can put that matrix in and then augment the other two columns, right? Agreed? Okay. But this one's not too hard to solve without actually putting it in our calculator. This says that this first one has to be 0 for both of them, doesn't it? Right? So if I want the coordinates for 7, negative 1, 0 with respect to B prime, or the coordinates of 6, 2, 0 with respect to B prime, both of those, the first coordinate is 0, right? If the first coordinate is 0, then the second coordinate for this one needs to be negative a half, right? If I already put 0 in for that one, then I get, stop. What are you doing? We put 0 in for this one, then this one has to be negative a half. The other one has to be 1 down here, right? And then finally, if this is 0 and this is negative a half, I would have negative 1 that I would move to the other side and make it a positive 8 and then divide it by 3. So I would get 8/3. This one, I would have a positive 7 and divide by 3, I get 7/3. So then I just make my matrix by putting in those as columns. Okay. So again, if you need to row reduce that to figure it out, that's fine. We figured we could do it in our heads for this one because it was triangular, so it wasn't so bad. Okay. So here's what our matrix looks like. So again, we put those coordinate vectors in there. Does that make sense? So let's see if we can you do a specific example, which is what the next one is, that makes things a little bit simpler. Because we're using standard bases. All right. So this one, we're going to go from going from P2 to P3. The process is that we're going to put x minus 3 in for P, and then multiply the result by x. Okay? So again, step one is to do what? If we're going to find a matrix with respect to the bases, what do we do first? Good. Plug in the basis vectors into the transformation. So again, the process here says put in x minus 3 in for x and then multiply by x, right? What do we get for t of 1 then? If I plug in x minus 3 into 1, what do I get? 1, and multiply by x, and we get x. There's not an x squared. Is that what your question was, Lee? Yeah, thanks. There's only 3 vectors in my basis. Sorry. When we plug in x minus 3 for x, we get, in the second case, we get, we'll get x minus 3 and then multiply by an x, we'll get an x squared minus 3x. That's exactly right. And in the other one, we'll have x times x minus 3 squared, which is x cubed minus 6x squared plus 9x. We okay with finding the outputs of the basis vectors? Literally just taking the x minus 3, plugging in for the x term, and then multiplying it by x when we're done. So far, so good? If you want to write this one out, this one looks like x times x minus 3, and that's where the x squared minus 3x came from. What's the next step after we do that?
Find the coordinate transition basis of the transform.
Good. Right, we take those outputs and find the coordinate vectors relative to the output basis. Well, here's my output basis. You've got 4 coordinates. What do they have to be in this case? Well, I need to get just a single x out. So it'll be 0, 1, 0, 0, right? No constant term, an x term, no x squared, no x cubed. What's the next one? Good. And the last one? It was positive now, wasn't it? Yeah. 0, 9, negative 6, 1. This one's a little easier because it's the standard bases for these spaces, right? So you have to pick off the coefficients. Makes that a little bit easier, doesn't it? So then when we create our matrix, first one is the first column, second one is the second column, third one is the third column. The last part of this asks you to calculate the transformation in 2 different ways. The first way would be to do it directly. That's one way to do it, right? Literally just plug it into the matrix. Or not the matrix, plug it into the transformation. The other way is to take your matrix and multiply it by the coordinate vector of your input. So I take the matrix we just found and multiply it by 1, 1, negative 1. That's the two ways to do it. So for Friday, go through those two ways and make sure you get the same answer when you're done. Now, of course, this will be the coordinates of what this is when you're done. Okay? Okay? So do that for Friday. Make sure you get the same answer both ways. That's the whole point of this, right? The whole point is we want to replace what the transformation is with matrix multiplication. It's a lot easier to program matrix multiplication than it is to try to program every other space into your computer and what the operations are. All right. We'll come back to this on Friday, as well as talk about inverses of linear transformations. And then next week, we're going to talk about eigenvalues and eigenvectors. So that just gives you an idea of what we're doing the rest of the semester. So have a good one. We'll see you.
Hey,
Hey.
I don't care if it's
I don't think you did either. Did you get the homework?
no.
Okay. So that's due Friday. Yeah, it says Monday, but I didn't give it out today. I thought I was going to give it out. I got your exam and I got a few homework assignments in here too.
Thank you.
Yep.
Track is leaving on Thursday for conference.
I know.